Good morning, everybody. Thank you very much for the introduction. It's really a pleasure to be here, to give the keynote in such an environment with such esteemed colleagues. It's really an honor, and it's also quite a challenge. So as I was thinking this morning and over the previous days about what I could bring to the session this morning, what I'd really like to do is bring a little bit of thought provocation and pick up on some of the themes we've just heard about the challenges facing pharma and think about how informatics can contribute in some of those areas, and perhaps be a little bit challenging on one or two areas. So I think you've all seen the title. I don't need to recap on that. So my presentation is really split into three main areas: an introductory section, a section briefly looking at what we currently do for R&D with some Roche examples, and then finally looking at a couple of examples looking to the future, where the potential is for informatics contributions going forward. So as I said, I wanted to introduce a little bit of challenge, maybe for us to question ourselves as we're going into the conference and the main sessions of the conference. So when you see this little image through the slides, it's just a chance to just think a little bit more deeply about the questions, maybe the proposals that I'm putting on the table, and maybe a chance for the discussion in the question time afterwards. So you've seen these graphs. You've just seen a couple of them now. On the left, we have the increasing costs of drug discovery and development, and reducing productivity. On the right side, kind of, if you like, a mirror image of the result of that, which is the failures that are coming in late-stage pipelines. Maybe 2/3 or so are actually due to lack of efficacy or lack of differentiation, maybe to be more specific. And I think pharma has an opportunity to respond in a couple of different ways to these problems. The first is, what we see a lot of, is to focus on the cost. If the costs are rising and productivity is dropping, therefore we must reduce our costs, reduce wastage, improve processes, and what have you. And of course, there's a lot of merit in that. On the other hand, one might look at it at a slightly different direction and say, it's more about getting more efficacious compounds through. It's about better decision making. It's about understanding the disease biology more deeply, so we don't end up in phase 3 with compounds that are simply not effective or not effective enough to benefit patients. And I think as we think about a contribution of scientific informatics into this kind of challenging arena, whether in biotech or traditional pharma, I think we should ask ourselves very carefully, with our activities, which of these things are we actually contributing to, and where are we putting our focus? So that will be one of the themes as we go through, to think about that in a little bit more depth. So I've introduced this word decisions. I hope you'll agree with me, the reason we're here, the reason we do what we do, is to enable decision making. All of our informatic contributions ultimately come down to that single factor. And at the moment, of course, it's still a human that makes a decision. So we can increase the value of the data, the information, with our systems, with our activities, with our contributions in silico science and what have you. We can support the derivation of knowledge ultimately so somebody in the R&D pipeline can make, or R&D projects can make a good decision. However, there's kind of confounding factors. So we can do our very best to make this objective, to make this rational. But when a human ultimately comes to make a decision, it's clouded, it's prejudiced by a number of things. Their previous experiences, the politics of the organization, short-term objectives, maybe their bonuses dependent on certain milestone decisions in that given year. So no matter how good we are, we're always going to have this kind of cloud. And you'll see this cloud appear a bit later on, because I think we potentially have some ways of addressing some of these problems. So decision-making in today's R&D project teams, of course, is not what it was when I started in the industry maybe 20 or so years ago. The volume, the complexity of information, data that's available to project teams is just astounding. And I think as humans, we have a couple of different ways of responding to this. Broadly speaking, we can embrace the complexity, and we can try and work through with all the information at hand to make the best decisions possible. Or we can be reductionist. And this is maybe one of my big themes is, at the moment, I think there's a temptation for scientists, particularly who have come from a traditional training, to be reductionist, to try and reduce the complexity of the information and the data that they have at hand so that they can make decisions. And I think one of our roles as informatics, scientific informatics professionals, is to enable scientists to not be reductionist, So I think you've all seen it. The reality of biology is on the upper picture here somehow. It's very, very complicated. It's full of dynamics, hugely complex. And yet when you talk with project teams about their biology, if you like, their biology of interest, or when they come and present their findings to the R&D committees, you often see models that are hugely simplified. And I think the risk there is that the simplification is actually also featuring in the decision-making, not just in the presentation. So here's the first kind of thought-provoking question. I think it's our role in scientific informatics not just to provide systems and tools, but really to be aiming to help scientists to avoid this reductionist thinking and also to avoid these prejudices that creep into decision-making. So I don't know if you agree with me or not, but that would be my first kind of big thought. So how do we do that? It's clearly a big challenge. So this is a cartoon that one of our chemists in Roche has drawn. She's a very talented artist, and it's kind of her representation of what it feels like to be a chemist in this hugely complex area. So I think one of our tasks is to help the scientists get to grips with this huge volume of data, this huge complexity of data. And often the challenge is underestimated in ways like this. We see these kind of images that are about, you know, the huge volume of information, and we see pictures like this. And they're grossly under-recognizing the problem, underestimating the challenge. So one thing I was sharing recently with colleagues within Roche R&D and beyond was just to give them a sense of what the challenge really looks like. So if we look at the PubMed citations, we have already over 20 million citations. If each citation is just a single sheet of paper, and you stack all the paper up, the magnitude is 5 times the height of the Empire State Building. So this gives it more of a physical reality, if you like. And of course, within each of those citations, there are many very complex assertions, findings, discussions, and what have you that allude to the complexity of our scientific environment. So, kind of set the scene. I'd like to give you a few examples now of what we're doing in Roche, just to address some of these issues. So the vision and mission of my organization, the informatics organization supporting research and early development, is we want to build an environment where our scientists and clinicians have integrated access. They can efficiently work with the data and the information at hand, and ultimately they can derive knowledge and predict outcomes. And although I don't mention decisions in this particular slide, it's all about the decision making at the end of the day. If they can predict outcomes, they can make good decisions. And really, we're all about driving and supporting scientific innovation. So yes, we still do a lot of those efficiency activities, but our real focus is on differentiation through innovation, which I think ultimately is the challenge of the industry, as previously mentioned. So if you look at a typical simplified R&D process, kind of linearized, hugely simplified here, there are many decisions at different points. The first big cluster of decisions is about selecting the right targets. So understanding disease biology, understanding the relevance of the biology to patient situations, individual patients or cohorts of patients, the druggability of the targets, and then moving into decisions around what molecules do you ultimately make, how do you design them, how do you test them, and then the translation to the clinic, of course. So safety considerations, formulation considerations, biomarkers, and what have you. And there's a lot of feedback, of course, within this. It's not a linear process by any means. So just taking some examples from the first area, how can we help our scientists kind of come to grips with the complexity of biology and all of that published data that we looked at earlier? So one of the tools that we've put in place is a very simple tool. I wouldn't really call it text mining as such. It's to support scientists when they're working with PubMed, with all these citations. And it's really a mapping of concepts. So we take the corpus, we map various concepts, so genes, diseases, companies, what have you, targets. And you'll all be very familiar with this. So we're mapping the concepts, not the actual terms, the specific terms. So we're using typical synonym vocabularies and what have you to do this. And this enables scientists to create queries. So in this case, we look for Roche in whatever form it's described. We look for melanoma as a disease area. And we get back our citations matching our query. And it's all marked up. So scientists can quickly see, you know, what's a company, what's a disease, what's a compound. And that's nothing new. I think most of you will have something like this within your organizations already. The nice thing here is then we integrate that with our gene target index. So if you were to click on a gene here, sorry, I'm pointing at the wrong screen there. If you were to click on a gene here or a disease, you immediately get into our vocabulary and our system's referring to that entity, that concept. So in this case, melanoma is just described in its ontology around disease. If you were to hover over the molecule here, this is one of actually a Roche development compound. For melanoma, you see the structure. You can link out to all information that we know about that compound, both within and outside of Roche. And if you click on or hover over the gene, you also see basic information about the gene and also the opportunity to connect into everything else we know about that gene within and outside Roche. So it's a nice, easy way for scientists to kind of work around their literature. It simplifies the process of pulling out key facts, if you like, key concepts from the literature. And then, of course, those concepts can be mapped in different ways and presented in different graph forms. So in terms of this deeper understanding of disease biology, which ultimately I think is how we make decisions that lead to efficacious compounds and differentiated compounds, I mentioned this, the Roche Gene Target Index. I think every company in the room probably has something similar. This is where we bring together everything that we know about genes, whether it's expression data in diseased or normal tissue, whether it's post-translational modification, whether it's splice variants, what have you. It's all there, easy for the scientists to navigate and work with. And then we have tools that are very specific to disease areas, like the Roche Cancer Genome Database. And this enables then the scientists of that particular area to delve a lot deeper into the molecular biology surrounding the disease. And I think the key value here is that we've pre-analyzed a lot of information for the scientists, and we've presented it in an easily consumable way. So I just have one example of decision support within the molecular design and production area. And the one I wanted to share with you is just the thoughts around in silico engineering of antibodies. So as you know, Roche has a strong capability in biologics, particularly in antibody therapeutics. And this tool brings together, ICETA, brings together data and information that helps the scientists to make decisions when designing new molecules, both internal and external to the company. So they may have questions about humanization, CDR grafting, the immunogenicity potential of the compounds that they're designing. And this tool enables them to map on those, if you like, those liabilities, those potential concerns, and to make